Hello, ROS developers, and welcome to a new presentation of a ROS project. In this case, we have Ahmed Yasser, who is going to do his presentation about the ROS basics in Python project. And then without much further ado, let's go with Ahmed. Are you ready, Ahmed?
Yeah, I'm ready.
Okay, then go ahead. Start with your presentation.
Okay, perfect. So let's get started with seeing the robot in action. So I'll run the code. So obviously, as we're probably used to by now, the robot, the first thing it's gonna do is it's gonna search for the wall. So that is what it's doing right now.
It's looking for the wall, right? It's turning.
Yeah, it's facing the wall, yeah. I think we've lost the right stream. Oh, it's running. So yeah, now it found the wall, positioned itself. I think the stream is a bit
Yeah, it looks like,
cutting out from here.
yes.
Yeah. So now it's going to start following the wall, and we can see on the terminal on the bottom left that it's kind of keeping track of its distance traveled.
Let's see how it solves it.
Yeah.
Okay, excellent. Is it getting lost? Is it going to recover? Yes.
Yeah, it's just
it's just what?
no, I mean the controller that keeps distance of the wall haven't really, done anything that really keeps it on a straight line.
Okay.
So you kind of see that it oscillates, but it would never lose the wall. Like
Yes.
you could keep this running.
Okay.
It's never gonna lose the wall. It's just gonna oscillate, but it'll always follow it.
Okay, yes. That's not something mandatory to have a very good
Yeah.
controller for following the wall, but to understand that there is a controller that takes the lasers.
Yeah, and I have a presentation. We'll go through it and kind of also identified what can be done in order to make it kind of better at following the wall or following it in a straight line. I just haven't gotten to doing that. But yeah, definitely. I mean, we'll go through this and the controller that I've implemented and what could be done in order to have it behave better.
Excellent. Great. It's about to accomplish one full lap.
Yeah. So it started around this corner right here. So
around here, more or less.
After the corner. So I've actually, the way I've done the code right now, it's not going to end. It's just going to say that it finished the lap, but it's going to keep going around. I don't stop the robot.
Okay. So, but is it going to
So
tell
right
us
here,
about the...
yeah,
okay.
yeah. So right here, you see, it sent all of the list of the odometries, and it said that the robot will continue moving. If you wish to stop it, you can kill the code. But it's just going to keep going around now.
Okay. Very good. Very good.
Yeah.
Great.
So let's stop the robot and can go through the presentation, and then we can go through the code. How does that sound?
Let's go.
Okay, perfect. All right, so just to kind of make it easier for me to explain what I've done with my project, I've done these basic slides. So kind of just an overview of what we'll go through, just a quick introduction, overview, and then we'll go through the three codes that make up the project, the wall following, the wall finding, and the odometry recording. And then we'll touch up on the future improvements. Like we've said, there are a few things that, if I was to spend more time on the project, I would implement them. So we'll discuss what those are, and then we'll just wrap up with a quick conclusion. So just kind of an introduction. So like we all know, this presentation is for the course project for the ROS Basics in 5 days course. The goal of the project, as we've seen, is to obviously implement a wall following algorithm that is able to navigate a mobile robot by maintaining a specific distance from the wall. We're using LiDAR data and odometry data. And for this project, we're working on the Turtlebot burger. So kind of an outline of the project. The entire project is broken down into three parts or three codes. The wall following code, which is actually the main script, which calls the other codes, and it kind of coordinates the wall following process. It manages, or the controller that it uses to actually maintain the distance with the wall is a PID controller. And for the second part is the wall finding service. This is called once in the beginning by the wall following code. And the purpose of this is to search for the nearest wall and align with it in order for the wall following code to then take over and maintain that distance. And finally, the odometer recording action is what we've seen was keeping track of the distance traveled by the robot, and it informs us when it's completed a lap as well. So let's dive into each one of these separately. So an overview of the wall following code, which is the main code in the project. The first thing that this code does is it launches the find wall service, which we will see in details. And that is the service that, as we've mentioned, finds the nearest wall and goes to it. It then also sends the go to the odometry recording action once it has positioned itself near the wall in order for the odometry recording action to begin keeping track of the distance traveled. And then finally, it begins the wall following procedure, which we will discuss in details in the next slide. Obviously, we're using the LiDAR, which is on the Turtlebot, in order to determine the nearest wall, the distance from the nearest wall to the right of the robot. And finally, as we've seen, this code communicates with the service and the action server in order to complete the whole project as an entire solution, basically. So for the wall distance controller, like I've mentioned, I've implemented a PID controller. So as we're probably all, I mean, I'm going to assume that everyone's familiar with the PID. It's basically, it has three elements to it: the proportional, the integral, and the derivative term. And basically, the input of it is the error, which is defined as the difference between the set point, which is 0.25 meters in this case, I've set it as, and the actual distance, which is measured with the LiDAR. The error is the difference between these two, and this is what gets inputted into the PID controller. The output of the PID controller is the angular velocity of the robot. So the proportional term, obviously, is just the output of it is directly proportional to the error. So this error, you multiply it by the Kp, which is the proportional gain constant, which is also used as a tuning parameter. And that multiplication, the result of that multiplication is the output of the P term. For integral, it's actually keeping track of the cumulative errors from the past loop iterations. The idea of this is to get rid of steady state error. So if there was a small, error which is not being picked up by the P term, the integral term, because it's accumulating that, it's going to eventually correct for it. And the Ki is the term which controls the integral output, and it's also another tuning parameter. Now, for the purpose of this project, as we'll see in the code, I've actually capped the maximum possible output of the integral term because it used to result in some very sharp turns at some point. So I've kind of capped the output of that. We'll touch on that a bit when we go through the code. Finally, the derivative term that takes into account the rate of change of the error, and that is what should try to smooth the movement of the robot as it approaches the line. Now, because I've implemented a single PID algorithm, which is taking into the account the distance and trying to output the rate of change, as we've seen, I found it very difficult to tune it using this controller to maintain a very straight line. Now, I'll touch in the feature improvement sections, I'll touch on why that is happening and how we can fix that. But for now, I mean, as you've seen, it does maintain the distance with the wall, but it kind of oscillates around this line. It doesn't hold it very straight. So this is the wall distance controller. This is what's responsible for maintaining the distance. Moving on to the next part, which is the wall finding service. So for the wall finding service, I've implemented a few things in order to avoid the robot from detecting any obstacle as a wall. We've actually kind of seen that, and we can play with it again if you want after we're done with the presentation. Even if you started very close to an obstacle, it is still going to go to the wall. To not go to the obstacle and assume that that is a wall. So we'll discuss how that is implemented. It's a basic algorithm, but kind of an overview of what the wall finding service is doing. The first thing is it uses the LiDAR to locate the nearest wall. After that, it turns the robot in order to face that wall and it starts approaching it. Once the robot is 0.25 meters away from the wall, which is the distance that it's trying to maintain, the robot will then rotate to keep the wall on its right. And this is when the wall finding service ends and the wall following code takes over. Now, like I've mentioned, in order to maximize the chance of detecting a wall rather than detecting another object, what I'm doing is kind of a moving average. So instead of taking one reading and seeing what's the lowest reading and pointing towards that, I'm actually averaging 80 readings at a time. And in order to even make it more likely to detect a wall, I'm amplifying anomalies. And what I mean by that, or sorry, discontinuities, not anomalies, I'm amplifying those. So if we look at this triangle as an obstacle, some of the, LiDAR rays, let's call them, are going to land on the obstacle. But within that 80 reading moving average, there will be some that will lie outside of the obstacle. So these readings, if they are greater than 4 meters and the LiDAR shows it as an infinity, so basically there is no obstacle within 4 meters, I won't input it as a 4 or whatever in the moving average, I'll input it as a large number or actually a 10. So by having these discontinuities, they really increase the moving average so much to the point that a wall which doesn't have any discontinuities will always have a smaller moving average, even if the obstacle is a lot closer than the wall. And by
Wow, that's
doing this,
very clever, very clever.
yeah, it's just a simple way. There are obviously more sophisticated algorithms you can do to detect discontinuities and everything, but I found that this works perfectly. You can start the robot really close to an obstacle and it is going to go to the wall. So if it works, why change it, right?
Awesome, awesome, very
So
good.
yeah, and just a quick thing which we'll see in the code. I mean, because I'm actually going through the entire laser scan multiple times while I'm searching for the wall to speed that up, I don't actually consider each item within the scan array. I skip 5, so I'm taking every 6th reading in the LiDAR. So it breaks down, it reduces the 720 readings to like 116, I think it was, or something like that. So it just speeds up the code in order to make the robot even able to like find the wall faster. We'll see all of this in code. So this is the wall finding service basically. Uh, the final part is the odometry recording action, and I think that one is, the simplest out of the three. What it does is basically, first thing it does is it obtains the current pose of the robot. It appends it to the list of odometry, which is what we send as the result when the action is completed. And then it keeps calculating the distance traveled in each interval of the code or in each iteration of the code. And basically it's calculating that obviously from my current pose and from the pose in the previous loop iteration. And I take that distance and you then append it, or not append it, actually add it up to the total distance traveled so far. And this total distance number is what is sent as the feedback in every iteration of the loop in the action server. And then finally, when the robot moves 6 meters, which is what I've identified as, pretty much one loop in my robot, and pretty like it's quite accurate. It does detect almost a loop, but it is a hard-coded number, and I'm not doing any detection to see that I have completed a loop. It's just when it completes 6 meters, it assumes that's one loop. And like we've seen, I decided not to code it to stop the robot because I maybe just wanted to keep going around, but it does notify you that it's done one loop. You can easily also make it stop, but I've just chosen to make it keep going. Um, so that's basically the odometry recording action. So moving on from what I've implemented, I want to touch on the future improvements a little bit and what I think can be done to make this algorithm a little bit more sophisticated. The first thing is I would implement 2 separate PID controllers for the wall following. And I'd split them. So the first one is actually kind of a track controller. So the input of that controller would be the difference between, my distance and the set point. And using that error, the track controller should output the heading. What is the heading of the robot? So in this scenario, which we see right here now, we can see that the robot is actually needs to turn to the right and its heading should point towards the set point. So that would be the output of the first one, the track controller. the heading controller should then take the heading, the desired heading in, and output the rate of turn. By that, I believe that if we implement these two and we tune them, the robot would be able to maintain the distance from the wall quite nicely. The problem with what I have right now is I'm measuring the distance and I'm trying to output the rate of turn. So it could be that, the robot is pointed in the right direction, but the distance is larger than the set point. So the robot, what it's going to try to do is it's going to try to turn as well, which doesn't make sense because, it's still heading towards the line. So it ends up having, it turns too much and then the distance increases and then it turns the other way. So it kind of oscillates around the line. So that's the problem I faced with having just one PID controller. So if I'd spend more time on this, I'd implement the two controllers, and I think that would make it stick to the line a lot better. Now, obviously, to implement this, we need to be able to measure the heading of the robot. I do this by just using the LiDAR. So in something like this, you can, identify at which angle in the LiDAR scan array the wall is hitting, and then, you can calculate the heading. The other thing is I'd implement a better way of measuring the distance by, again, implementing some sort of, moving average or something like that, just to have better inputs in terms of distance and in terms of heading. So by implementing these three changes, I think you'd be able to get the robot to really hold a nice line when it's following the wall. The other thing I would change or I would upgrade is in the find wall service. So right now, it always turns to the left, like it identifies where the wall is, but it's scanning always turning to the left. It's a small change, but if it can turn in both directions to find the wall, it would end up finding it faster, because right now we'll see in the code it actually turns always to the left to face the wall. But if the wall is almost to its right, it's still gonna turn a full loop to find it from the left side. So this is also another small change, if you can make it detect which direction the wall is and turn towards, that would speed up the wall finding service. Finally, for the wall finding in the find wall service, right now I'm doing the moving average, as we've seen. We could definitely implement a more sophisticated algorithm that can actually detect discontinuities and identify that, this is a wall with no discontinuities, or, having some more sophisticated algorithm to identify that it's a wall would probably make it so that it is more general and it can behave just as well in other environments. In this environment, though, the moving average has worked fine for me. It's never gone to an obstacle. But, if you implement a better wall finding solution, you probably have it so that it's more general, and no matter which environment you put it in, it'll always identify a wall. So these are the three main improvements that, if I work on the project further, that's what I would start with working on in order to make the solution more robust. So to wrap up the presentation, as we've seen, and we can give it another run also towards the end. The code works reliably. I've tested it in both the simulated and the real environments. I've never had any issues where it ran into the wall or it didn't find the wall. It works, and you can leave it running for an hour. It's not going to be a problem. The wall following operation, though, as we've mentioned multiple times, it can be made smoother if we've done the upgrades that I've mentioned in the previous slide. But overall, I found this project to be quite simple and fun, and it kind of made me implement what I learned through the code, which is really nice of you guys. I think that is kind of a perfect project to implement at the end of the course, because it kind of put everything together that we've learned, and I really enjoyed doing the project, actually. So yeah, that's it with the presentation. Do you have any questions on it before we go through the code, or you want to go first through the code?
Okay, yeah. Can you show us a little bit how you have organized your code?
Yeah, so you want to go through to the code, basically.
Yeah, but in a general sense, because we are not going to go.
Okay.
So I want to see the structure. So where did you put the action server?
Okay.
Where did you put the service? And where is the main loop that is, the main loop, the main code that first calls the service in order to align, then continues with the wall following, and then so the callback, for example, let's say the callback for the action server, when it finishes that produces the output. So, but just in the general sense, let's not go into details.
Yeah, of course. Let's do that. So this is the code for the wall underscore follower .py. That's the main code. That's the one that does the wall following, but it also calls the find wall server and the ODOM action server. So over here, I mean, obviously the imports and everything. This is just to publish the command velocity. This is the first part where we actually call the find wall server. So the find wall server is what's in this code, and we can skim through it after we're done with the main one. So that's the first thing.
Wait a second. I only have 2 questions for you, and here is the first one. So why are we putting the find wall algorithm inside a ROS service? Why don't we put it there, just straight into the core, into this code, inside the wall follower code?
Yeah, I think there are like 2 reasons I would say to this. The first simple one is obviously the organization of it, because you don't want everything to be in one large code. But obviously it also makes it so that you can easily call that multiple times or from multiple nodes, and it's just there, it's a service that's implemented once.
Perfect, very good.
Multiple nodes can call it.
Yeah, it's important for me to see if you have understood this, because then you are going to use this concept also in your programming of other robots. When to decide when to put a service or some code inside a service, and it's what you mentioned, is because you want to call it several times and from multiple nodes, not just from that node, which is a wall follower, but maybe another program inside the robot needs to align the robot for some other reason. So, for example, the robot, I don't know, when it reaches the end, then it has to present a message to the people that is in front of the wall. So it has to align again to the wall. I don't know. So the node that will show the message to the audience, then we'll need to call also the find a wall service.
Yeah, exactly. So we've implemented it once, and you can call it multiple times again within the same node or multiple nodes.
Multiple nodes, exactly.
Makes the code a lot more concise and cleaner. So that was your first question. What was the second one again? Sorry.
No, the second is going to be later. The second question.
Okay.
Yeah.
Okay. So so this is where we're calling the find wall service, and it waits for the result to come before it proceeds with the code. So it actually holds the code there until the find wall service is done, and then it proceeds with the rest of the code. For the record ODOM, it's actually here, and in order to not hold up the code, it kind of has these 2 callbacks. One is for the feedback. When a feedback message is received, all it does is it prints it, and when the final result is received, again, it doesn't stop the robot in this case. It just prints the result, and it tells you that the robot will continue moving. You can set a flag here to have it and stop the robot or something, but I chose not to do that. So this is where it calls the record ODOM action server.
Okay, so here comes my second question.
Yeah.
And why do we put this code into an action? I mean, the recording of ODOM, why don't we do that inside this wall follower?
Yeah, so first, why action, why not service? Obviously, because with the server, it holds up the code until it finishes it. With the action, it's kind of running in the background. So that's why it's an action, not a server. Why is it an action, not just in the code? It's similar to the service, it's something running on the side again, cleans up your code rather than having everything in just the code. And every time I wanna implement the odometry, I have to put that same code again. So it's just a cleaner way of doing it, and it runs on the background. It's doing its own thing, and it's just sending me the feedback and the result when it's done. It doesn't hold up my code in any way.
Excellent, excellent. That's it, exactly what you said. Very good. I can see that you have really understood the concepts. Very good, very good. Continue. No more questions. No more questions. Just show us how it ends this, and then we are done.
Yeah, sure. Here is the PID implementation. You're taking the time in order to do the derivative and the integral. You've got your gains here, the 3 gains. This is what you'd use to tune it. And then this is the callback. This callback is actually called when there is a new scan data. And this is where the main code is happening. If we skim through it to the more important parts, you can basically see here that it is checking the distance from the right wall, and it's basically just implementing the PID. I don't know if you want to go through the details here, but it's just
No, not
calculating the PIDs,
necessary.
calculating the error, and
Not
yeah, you're
necessary.
doing the KP, KI. Yeah,
Yeah. So it's the code of the controller, and then
yeah.
what I would say
Mhm.
is a suggestion. Okay,
Yeah.
is for this callback. So you usually the callback code should be a
Mhm.
very short code.
Short.
So
Mm.
you should not put your control inside the
Mhm.
callback. So the
Mm.
callback usually has to be just to capture the data that it's providing
Mhm.
from the topic, and then put into some variable that then in some other part of your code is going to be used, because the callback should
Mm.
provide the end of the callback should be very fast in order to don't skip, the loop of
The
refreshing,
new.
because it's being called very, very fast. So
Mm.
you are missing some calls, some messages, or you can have a queue, and then you will be processing data that doesn't correspond to the
To
real
the latest.
situation now, because they
To the
have been
latest.
queued. Yeah. So
Mm.
usually it's better to put all this code into the while loop control that you have in your main.
Mm.
Okay.
That makes
Yeah.
sense, actually. Yeah.
Here everything is very fast, and the robot is not moving fast. So
Yeah.
you cannot detect this, but it's for pro programming. Okay. So when you go to another
Mm.
company and use those skills, then try to do it this way better.
Yeah, makes sense. It's a very good suggestion. So
Great.
yeah, that is definitely the case. Uh, okay.
And yeah, and
And
that's
then
your control loop. Actually, while not ROS shutdown, this is your control loop, right?
yeah, that's very short. So I've done it the other way around, actually.
Yeah, okay. Okay.
Yeah.
Okay, then. Wow, I'm amazed. Awesome presentation, Ahmed. Really,
Thanks, man.
really,
Thank
it's
you.
impressive, your presentation in all the senses. First, in the behavior of the robot, so it works. Also, second, on your code, organization, how you have done it. Third, on your slides presentation. It's impressive.
Thank you.
So really, and I can see that you have understood all the concepts. So of course, you have passed the project presentation stage, and then you are going to receive your certificate in a couple of hours at the platform, and then you can share them on LinkedIn, download as a PDF, etc. Congratulations. I want
Awesome.
to give you one thing. I'm impressed about your presentation, how well
Mhm.
structured it is, and how much detail you have put into the images and the structure of each one of the slides. So you have one slide and the other one. So it's so in one slide you have the text, and then you have the image that you have prepared for this presentation specifically. So awesome. One small advice for improvement, okay? In
Yeah,
that
please.
case is about the text. It has too much text. You should reduce that,
Mm.
I would say, yeah, this
Yeah.
by 5. So you have to divide the amount of text that you have and divide by 5.
Yeah.
Just big points. And
Mhm.
that's all. Because all the rest, you are explaining. So the people doesn't have to
Yeah.
be reading. You just put the main points, 3 main points, big letters, and that's it. But it's awesome, and also the style is very, very cool, very professional.
I'm glad you like it.
Yes, very
All
good.
right.
Then,
Thanks a lot, man.
thank you very much. Excellent project. What is your next goal?
I kind of, I'm actually working a bit with Rust. That's why I wanted to do this course. I probably go through a few of the other courses to get a little bit deeper into it, and the TF, the transforms,
Mm,
the SLAM. So I'll probably go through a few other courses,
okay.
but I'm doing other courses, on the side as well for
Uh-huh.
other topics. So I'm kind of balancing,
Yeah, I understand.
so I don't get
Okay, okay.
yeah.
Then
So,
please
but yeah,
don't miss the
definitely.
one of TF. So TF is very, very
Really?
important in ROS.
Mm,
Yes, it's super
okay.
important in ROS.
Mm,
And if you want to understand, it depends on your background, okay? But then in order to
mm,
understand TF, you should understand also the URDF. So if you already know a
mm-hmm.
little bit of URDF, then go straight into TF. But if
Okay.
not, you will have to do URDF and then TF. Because the TF is a key concept in ROS and in robotics also. It's about the
So you
different
would
frames. Hmm?
you would suggest for that to be the next course that I
Yes,
do?
yes,
Okay,
yes.
done.
TF is a complex concept to understand,
Mm,
and it's key in ROS specifically and in robotics also in general. But
mm,
because it's about the different frames and how to move into the different frames inside a single robot.
mm,
So how to reference information from the frame of the head of the robot, for example.
mm,
How to, for example, the head has a camera and is detecting a mark. The mark is I don't know 1 meter, but it's 1 meter from the camera,
from the head,
not from the center of the robot,
not
not
from
from
the
the
head. Yeah.
hand. So you have to do the conversion of those to the
Okay.
hand, so the robot knows how far it is from the hand itself. And
From the relative to move it from the relative frame of reference to basically the global one. So
yeah, or
reference
to
to
another
yeah,
relative also.
yeah,
And
yeah.
this is all those matrices that you study in robotics
Mm,
and doing the transfer from one frame to another. But TF
yeah.
does all this work for you
Mm,
automatically.
okay.
So it's a huge improvement, and then you need to know how to use it.
Yeah. Perfect. So I'll do that next then.
Great.
All right. Thanks a lot, man. It's been a pleasure.
Thank you very much. It's been my pleasure to be leading your presentation today. It's awesome. It was awesome. It's so awesome. I'm going to take
Thank you, man.
with your permission, I'm going to take this as the example for the future students. I will tell them, watch these presentations if you want to know how to do the presentation.
Awesome. Perfect.
Thank you very much, Ahmed.
All right, man. Thanks a lot, man.
Thank you. And for
Have a
all
good
the
day.
students over there, then here we are waiting for your presentation. So what are you waiting for? Come on, you can be like Ahmed and get your certificate, show on LinkedIn that you have won it, and also then get a better job programming robots. So we are waiting
Yeah.
here for you, and see you on the next presentation.